So welcome to physics class, semiconductors, Riju and PSK classes. നമ്മൾ ഇതുവരെ ഡയോഡ് പഠിച്ചു, ട്രാൻസിസ്റ്റർ പഠിച്ചു, ട്രാൻസിസ്റ്ററിൻ്റെ സർക്യൂട്ടിൽ കിർച്ചോഫ്സ് വോൾട്ടേജിൽ അപ്ലൈ ചെയ്ത് ഇൻപുട്ട് ഔട്ട്പുട്ട് ഇക്വേഷൻസ് എഴുതാൻ പഠിച്ചു. ഓക്കെ, ലാസ്റ്റ് ക്ലാസ്സിൽ ട്രാൻസിസ്റ്റർ ആസ് എ സ്വിച്ച് മീൻസ് നോട്ട് ദ ടക്ക് സ്വിച്ച് അല്ല, voltage changes from one level to other level. That change, that's what we call as switching. How to use a transistor for switching operation, we studied about that too. So today I am going to give you one more application of transistor, but before that a quick review of the essential concept that we need. This is a common emitter transistor configuration. Emitter is common. This is an NPN transistor. You can see the polarities. Okay, the input is taken across base and emitter. Input is taken here. This is where you give input, and this indicates the input across these points. Okay, so better to have an arrow mark here. Output is taken between the emitter and the collector. So this is where you take the output. VO is the output. By writing Kirchhoff's voltage law, for the input we can get this equation: V input equal to IBRB plus VB. Okay, that you should be very clear. V input is given by IBRB. IBRB is what? The voltage drop in this resistor plus the voltage between the base and emitter junction, that's VBE. Similarly, if you apply Kirchhoff's voltage law for the output circuit, we will get output. Output actually is the voltage across collector and emitter, VCE, and that is given by VCC, which is the battery voltage there, minus the drop in the collector resistance. So these are the input and output equation. You have to be thorough about this thing. Okay. Whether it is NPN or PNP, this equation will not change. For NPN and PNP, only this battery polarity will change. The equations will remain same because the current reverses, current direction changes. Now, transistor as a switch. Last class, yesterday, we saw this. For transistor acting as a switch, we should know that there will be no external input. External input is not there. There is no external input. Okay. This voltage itself is taken as the input and output. So here, when the input is very high, we proved that output will be very low by using this equation. Okay. Now, if the input is low, input low means you get a high output. So that is the meaning of switching. If you call a low input, input low, okay, Vi low, if you take this as 0 and if you take a V input high as 1. 0 stands for one level, 1 stands for the other level. If V input is low, and we proved that V output will become high, that is taken as 1, and when V input is high, then V output will become low, and that is called 0. So you can actually write these zeros and 1 in a table like this. You can just say that A is the input and say Y is the output. A stands for the input you give and Y stands for the output you take. I don't know why output is written as Y everywhere, but universally it is like that. Output is taken as Y. Now input 0 and input 1. There are two possibilities, 0 and 1, and the output will become 1 and 0. Okay, that's what I say. We normally write using a Boolean algebra, we write Y is equal to not A. Y is not A. Not A means there are only two possibilities, 0 and 1. Y is not A means if A is 0, other than 0 there is only one state, that is 1. If A is 1, other than 1 there is 0. That's why it's called Y is not. So we call it as a not operation, not. It's also called inverting. You are getting the inverted output. Invert. Okay, that's what we studied about a switch. Now, transistor has got one more application, that's called amplification. Okay, amplification means increasing the strength. Increasing the strength means current, voltage and power. Increasing the strength. That's why we have defined and studied these different equations. So the current gain, you see this current gain is written as current gain, It's called this A stands for amplification, increasing the strength. Amplification of current. It's also known as beta, and see the way we write beta AC. Sometimes we write beta DC. It has nothing to do with the normal AC and DC. This is for a variation in the value. Variation. That means you should know that when the base current is IB2 and base current is IB1, you are changing the base current from one value to the other value, then correspondingly collector current also will have two values. For first base current, first collector value, second base current, second collector value. This is what we write as delta, change in the collector current by the change in the base current. That's why we call it as AC. AC stands for dynamic change. Dynamic, it's a variation. But beta DC means we are not taking a different ranges, rather we will have one base current and correspondingly there will be one collector current. You take the ratio directly, one base current, one collector. That's why we call it beta DC. For all of them this is possible, AC and DC values, fine. Anyway, this is the current gain, and for a common emitter configuration this beta is greater than 1. So that means the change in the collector current is greater than the change in the base current. Now voltage gain. You have an input voltage and an output voltage, as we said earlier, and if you take that ratio we get the voltage gain, which is AV, and voltage gain is given by beta into R output by R input. Normally in simple circuits, R output means collector resistance, R input means the base resistance, RB. But of course, when you go to higher levels, these things can change. This is a very simplistic thing. Even with this simplicity, you are not able to follow this. So think about the complex side of this. Okay. Don't worry, all those medical batch students, you have nothing to worry about this one. This is the end, this is the start of it, this is the end of it. But for those engineering branch students, there is a long way to go. If you go to any engineering college, any branch, you have to study this again. Okay. Now the last one is a power gain. Power gain is beta square into Rho by Ri. It has got various equations here, but this so you remember it is very easily. And for common emitter configuration, both AV and AP is greater than 1. This is greater than 1. This is also greater than 1. In fact, this beta is greater than 1, and beta square must be a larger value. Suppose you get beta equal to 10 to the power 2, 100 times. That means the change in current is 100 times. Then power will be 100 squared, 10,000 times. That means the common emitter configuration gives you a very large gain in power. A small input power can give you a large output power. Bapre, small input power and a large output power. So does it violate conservation of energy? Are you creating energy here in a transistor? We will see that. Anyway, I said this is the ability of common emitter configuration, that you can get more voltage, more current and more power. That's what we use in an amplifier. Right now when I speak, I am speaking to a microphone. You can see that this is a microphone. When I speak to this, I am producing a small variation in the voltage. It's actually there is kind of an induction, voltage changes, and that voltage change is picked up by some circuit in that camera. Okay, and that camera has a circuit, and that circuit will have a transistor somewhere, and the transistor, this will go to the base of the transistor. That means you are giving an external input which was not there in the switch circuit. Switch circuit il idu undayirunilla. Ivide nammal oru external input kodukkunnundu, and you see a capacitor here. This capacitor, the purpose of the capacitor, I'll tell you in the beginning, is to remove any steady voltage in the input. Steady means direct DC. In the input you want only a varying one, like when I speak the voltage actually keep varying. Okay, you want only the variation of the voltage here. So that varying voltage is given here in the input. So in a simplistic way, I can represent the input as a sine wave. Suppose you have a wave like this. Is this a sine wave? Of course it has got a sine wave plus are DC. It's a combination of sine wave and a DC. You don't want this DC to come into the circuit because that will change the biasing voltage. So to remove this thing, you use a capacitor. You can see a capacitor outside also. To remove, you see, if you don't use this capacitor, this DC voltage will come to the output. So you need to prevent those DCs. That's why we use a capacitor. Okay, if you want to understand how a capacitor blocks it, go back to your chapter AC and see the capacitor has got a reactance which is inversely proportional to the frequency. Frequency of DC is 0, so reactance will become infinity. Capacitor will not allow DC to flow through that one. It will allows only the variation in the current. Okay, anyway, now this input is given here. Okay, this input is given here. So any variation in the input, if the input increases, the base current will increase. Okay, if the input voltage increases, the base current will increase. When base current increases, there will be a large change in the collector current and that will change the output voltage. Okay, what is that equation? Equation for output is like this one, V output equal to VCC minus ICRC. Okay, so what will happen? Okay, and the input equation was okay, fine, VBE plus IVRB. Okay, now I'll tell you. Now see, when the input voltage increases, I can write here, when input voltage increases, base current will increase. Okay, we discussed the same thing in the section of switch also. Base current increases. When base current increases, when input increases, this base current will increase. When base current increases, from the characteristics, you can see there is a large change in the collector current. Okay, when collector current increases, you can see this ICRC, that product will increase. When that product increases, the difference VCC minus ICRC will decrease. Work out. Input voltage increases. Okay, this VBE remains pretty constant. Only variation will happen in IB, RB, resistance will not vary with current, so IB, the base current has to increase. This you will get from the input characteristics. Now, when the base current increases, you go to the output characteristic, you can see that when the base current increases, there is a large change in the collector current. Okay? When collector current increases, what will happen here? Okay. When collector current increases, what will happen here? Assume that VCC is 10 volt minus IC is 1 milliampere into RC is 1000. Oh. So 10 minus 1 milliampere. See, 1 milliampere is 10 raised to minus 3. 10 raised to minus 3 into 1000 will give you 1. Right. So this will give you 10 minus 1, which is equal to 9 volt. Now imagine collector current, it was 1 milliampere. Assume that collector current changes to 2 milliampere. What will happen? What is the new value? If the collector current changes, what will be the new value? The new value will be 10 minus. Instead of 1, you write 2 milliampere, 2 into 10 to the power minus 3 into 10 to the power 3 resistance. Then you can see that 10 minus 2 equal to 8. So see, when collector current increases from 1 to 2, the output voltage actually decreased from 9 to 8. Fine. That important point you should have to carefully note. So what I am telling is that when you input, see, when I speak to the microphone, there is variation in the voltage applied here. That will vary the current in the base, and that will vary the collector current, and that will vary the output voltage. This is how it varies. Fine. Now, these are the equations. Mathematically, you are going to do that. Okay. Now, this is from NCERT. I just take it from directly from NCERT. Okay. So let us write the output, the output voltage. V output is nothing but VCC minus ICRC. Now tell me, out of this, which are constants, which are variables? This VCC is a constant, RC is again a constant, only IC is variable. Fine. So if I am differentiating it, or rather if I say VCC will not change, the change I am writing changes. Okay. I am writing about changes. What are the things that you can change? The output voltage can change, delta VO. I am differentiating it. This will become 0. That means VCC will not change. minus, in this parameter only collector current will change but the resistance will not change. So this is actually a derivative of that first equation, which actually is used to tell you that when collector current changes, the voltage output changes. Let us do the same thing for the input side. For the input side, we have the equation VBB plus IBRB. And what can change here? Output voltage, if the input voltage is changed, the change in base voltage, that is negligible. So we will take it to be 0. Here the resistance will not change, only the base current will change. This is what we have here. Okay. So the input again you can see here. This delta VB is negligibly small. So delta VI is IB into RB. This is the output equation, call it as equation 2, this is equation number 1 or any number, no problem. Now what do you want? You want to check whether there is a change in the output voltage. What you do is that you will divide equation number 2 by equation number 1. And what will I get? I will get delta VO, change in the output voltage by change in the input voltage. This is nothing but your voltage gain, AV, and this is given by. If you divide it, you can see that there is a negative sign, delta IC into RC divided by delta IB into RB. And what is this parameter here? Delta IC by delta IB is nothing but beta AC. Beta AC into R of the collector by R of the base with a negative sign. This is the voltage gain in the common emitter circuit. Okay. Now you can see that the collector resistance is greater than the base resistance and the BAC is always greater than 1. So it says that the change in output voltage will be greater than the change in the input voltage. That means if you make a 1 milliampere change in the input, there can be 1 millivolt, it should be a potential difference. If you change 1 millivolt input, if you make a 1 millivolt change in the input, there can be 100 millivolt change in the output. Is this good for us? Yeah, by giving a small change in voltage, you are getting a large change in the output voltage. So this means that it can work like an amplifier. It can increase the strength. But there is a negative sign. There is a negative sign. It says that when the input increases, the output numerically decreases. Fine. That means there is a 180 degree phase difference between input and output. This is an important point in common emitter configuration. 180 degree out of phase. Input and outputs are 180 degree out of phase. Don't worry, this will become more clear when you see this graph. Both NPN and PNP does this. You give an input voltage which is varying like this one, you get an output voltage which is quite opposite. Okay, I'll explain that. Okay. This is the input voltage, V input, and you are going to mark the output voltage. Very careful. This is one cycle. This is one cycle, one period. When the input increases, we saw that when input increases, base current increases, collector current increases, but the output voltage decreases. You remember that we did that numerical example, 9 volt, then it was 8 volt when collector current increases. So this becoming more and more positive, this will become more and more negative like this one. But the advantage is that this has got a small change, but this will have a large change like this. There is no change in the time period. That means the frequency of the signal is not affected. In an amplifier, the ratio between the output frequency and the input frequency will be the same. That is why even when you amplify a sound, the sound remains the same, only the strength increases. When I say hello, you hear it is hello, but maybe a louder. If there were a change in frequency, then the pitch would have been different. When I say hello, maybe you will hear it as hello. This is not possible. Frequency will never change. Maybe if frequency changes, then a male voice may appear like a female voice or vice versa. Suppose you speak like hello, how are you? Then the output will become like hello, how are you? That is frequency change. But here there is no frequency change, only loudness increases. When I say hello, you will hear hello. Same sound, large strength. That's what the peak indicates. It's going positive, it's going negative, but see, for getting power you square. So when you square, even the negative become positive, right? So power increases always. There is this input, this output, there is 180 phase reversal. That's it. Okay. These things are put here in this note. This for your note writing. You can write note. When AC signal is fed to the input, AC means a variable one, the forward bias increases during the positive half cycle of the input. This results in an increase in IC and a consequent decrease in VC. Not VC, it should be V output, okay? V output. Thus, during the positive half cycle of the input, the collector current becomes less positive. That means input increases, collector voltage decreases. Then this is written for the negative half cycle. Hence, in a common emitter amplifier, the output voltage is 180 degree out of phase with the input voltage. In theory examination, normally they asked this, but now since this part is not there in the CBSE theory, you may not have to answer this, but for entrance you have to remember this. But for those state students, state syllabus students, these points can be asked in the board examination. Okay. Now to make the concepts clear, let us do few numericals on transistor. Okay. First one, in a transistor, the collector current is always less than the emitter current, because if you had noticed during the working of a transistor, you have seen this. If you take an NPN transistor or a PNP transistor, let's say this is NPN, this is PNP. In NPN transistor, you have large number of electrons here, and there are few holes. Here it is the reverse, large number of holes, holes here in the emitter and few electrons in the base. This is emitter, this is base. Emitter, base, collector, collector. What happened is that large number of electron will migrate to the base, but few of these electrons will be combining with the electrons available. So only the remaining electron will reach the collector. Important point. Suppose 100 electrons starts from the emitter, 10 might be lost in the base, only 90 will reach the collector. Okay. So in that case, I said 100 electrons started out, but 10 lost, remaining is 90. In such a situation, the collector current is due to 90 electron, the emitter current is due to 100 electron, base current is due to 10 electron. So we can say the emitter current is 100%, then the collector current will be only 90% of the emitter. Similarly, the base current will be only 10% of the emitter current. Okay. This is the reason why the collector current is always less. The same thing happens here. Holes will enter the base junction. Few electron will be combining with the holes. Only the remaining hole will reach the collector junction. So the collector current is always less than the emitter current. The reason, a few electrons are lost in the base and only remaining ones reach the collector. Okay, this is about an NPN transistor. That's why they have given electron. If it were a PNP, it would have been holes. Anyway, few of them are lost. That is why we make the base very thin and lightly doped. We don't want a large number of electron to be lost there. We want only a few number of electron to be lost. Only then the transistor will work as we wish. Fine. See, which of the following statement pertains to only PNP transistor, which is applicable only for PNP transistor, not for NPN. See, few of the statements are applicable for both of them. Okay, but we want the one only correct only for PNP. What is the first one? The emitter injects holes into the base region. That's correct, right? So if you know the working of a PNP as well as NPN, which we discussed in the previous question also, consider this as a PNP transistor. So this side is P, this is N, this is P, and you bias this as, you need to bias. Active operation means this should be forward bias, so this must be positive, this is negative, so that must be positive, and then here you connect them like this. This is the connection in the case of a PNP transistor, and for NPN transistor you can go and refer your notes on this. NPN, this is connected to the negative, this is how you bias it. Fine. Now emitter injects holes into the base, that's correct, because in the P side you have more number of holes, so these are getting pushed into the base. This statement is correct. But in the case of NPN, you have electrons here more and they are getting pushed into that one. So that is not applicable for NPN. This is applicable only for PNP. The electrons are the minority carriers in the base region. See, in the case of PNP transistor, base is N type where electrons are majority. For NPN, base is P type where electrons are minority. So this statement is applicable for NPN but not for PNP. Third one, emitter base junction is forward biased for active operation. You should see that the emitter base junction, this junction is a PN junction where P is at higher potential than N. So this is forward biased. Okay. Now here, this is the junction, and N is connected to negative, P is connected to positive. So this is also forward biased. So this is correct. This is correct for both of them, not only for PNP. So this is not our option. It is a correct statement, but it is applicable for both NPN and PNP. So we cannot take it. So I will say, when I say wrong, this statement is completely nonsense. But for PNP that is not correct. But this emitter base junction forward biased, it is applicable for both the NPN and PNP. But here we want only to PNP. So you can't choose that one. The collector is at a negative potential for active operation. Collector, you can see this is collector. Collector is at a negative potential, means collector is connected to negative. So this is at a negative potential, whereas this collector is at a positive potential. So that statement is applicable only for PNP, not for NPN. Okay. So fourth one is again correct. So for PNP, which are correct? 1 is correct and 4 is correct. Only for PNP. So is there an option like that? Yeah, 1 and 4. That is our right option. But understand that this option 3 is correct for both NPN and PNP. That's it. Okay. From there, in common emitter mode, the input characteristics of a transistor is a variation of, you studied that one, input characteristics. Okay, that is a graph, input characteristics. It's common emitter. In common emitter, VBE is the input voltage and IB is the input current, and you saw the graph was like this. It is a variation of base current versus base emitter voltage when the collector emitter voltage was a constant. This was kept constant. Okay. So that's your option. IB against VB at constant VCE. That is the answer to that question. So children, study the theory, work out questions like this one. Do not go to very high level of questions and all, base questions. First thing you need to do is do simple base questions. Do that. See you in the next class.